Okay, we're back to do another identifying the major species in a weak acid or weak base when they're at equilibrium. We're doing a second one because the previous one, what they did is they added a strong base, and what we discovered is when we added that strong base, or was it a strong acid? I can't remember which. It overran whatever the weak acid was, and so you just ended up with extra. So we're going to try and do it this time where it's a little bit different here. And as is always the case, whenever we add a big dog, so that would be a strong acid or strong base, to a weak, you're going to have to deal with a stoichiometry problem. So, as always the case is, number one, do stoich. And the stoichiometry is always going to be in millimoles or in moles. And then two, equilibrium. So then do an equilibrium problem. Now, in this particular case right here, we should make note of how much of each of the things that we have that are interacting with each other, but we need to know how they're interacting. So if we take a look right now, we have HF, and to HF, we are adding KOH. Now, I would never, in a regular problem, include this K in here because the only thing that really matters here is that this OH minus is going to attack and rip off hydrogens over here. But because they have an other category, we know that this K, which is going to be a spectator ion, is going to appear on the other side as well. So we're going to leave it in there for this, but don't be frightened by it. And don't think it does anything. In fact, it might be really good to write K plus over here just so you don't accidentally do something with it and try and react it with something. So then you have OH minus, which is something that we're pretty familiar with. The OH minus, what is it going to do? It's going to grab a hydrogen off of this. And what's that going to leave? It's going to leave us with an F minus. So let's do that. And we're going to end up with F minus plus H2O. Now, where do we go from here? Well, let's take a look at what they've given us because we have to do this in terms of millimoles or moles. Now, they give us right here, and it's pretty clear, they give us 0.3 moles of KOH. So what are we going to do? We're going to put 0.3 moles right here. And then they tell us that they're giving us 0.9 molar and 1 liter. So just a gentle reminder, if you ever want to figure out the moles of something, moles is equal to molarity times volume. And so since moles is equal to molarity times volume, and we know 0.9 is our molarity and 1 is our volume, we know that we have 0.9 moles of this. So what that means, if we're doing an ICF, that's initial, change, and final, remember, these two things right here, they're going to go to war, OH minus and the HF. And they're going to keep on going until all this OH minus is either used up or all the HF is used up. Either way. In this case, we have only 0.3 moles of this and we have 0.9 moles of this. So where does that leave us? Well, that means that we're going to lose 0.3 moles here and 0.3 moles here. And over here, we're going to gain 0.3 moles. So at the end of all this, we're going to end up with 0.6 moles left of our HF, none of our strong base, and our conjugate acid we're going to have went from 0 to 0.3 moles, and we're going to have some H2O, which they say to ignore, and we're going to have some K+. So let's take a look at what we have here for sure. We know that we have an acid, and that's HF. So what are we going to write over here? We're going to write, well, we got HF. What about bases? Well, if we take a look at this base right here is 0, so we don't have that, but don't we have 0.3 moles of our conjugate base right here? So we certainly have that, so we're going to write F minus. Then what are the other things we have? Well, the only other thing that we have here is that this K plus that was floating around as a spectator ion, and that's why we're going to write it in here as K plus. So let's take a look at the second scenario here. And this is one that they will not ask you on the AP exam, but just so we can relate to this, let's try and write it out here. Again, we have a strong base, but this time it has an Na plus in front of it, and it's getting thrown into a solution that has 0.5 molar HF and 0.5 molar KF. Now, one of the things you need to be aware of is that OH minus will only go after an acid. If it had been an H plus, like HCl had been added, then it would go after the F minus. And again, spectator ions like the Na and the K, don't get freaked out by them. But let's just write an equation of what actually is happening. I'm going to include variables that I normally would not do. But I know that OH minus is going to go after the HF. So I'm going to write HF, and I'm going to have, and because I know that there's going to be other things in here, I'm going to react that with NaOH. But in reality, and this is a one-way street, in reality, I know this Na plus is going to do nothing. So I'm going to write this over here as Na plus, just keep it out of the way. And then I know the OH minus, since it's a strong base, is going to grab the hydrogen off of this, and it's going to form a pretty innocuous thing, H2O. And what's going to be left here on the HF is going to be F minus, and we're going to have this. So whenever we do any sort of strong base or strong acids, in this case it's a strong base being added to a weak acid, we have to do stoichiometry first. That's our rule always. So we're going to do ICF, initial, change, and final, and we're going to put the moles of each thing in here. Now they've told us here that we start off with 0.3 moles of the NaOH, but now they gave us 0.5 moles and 1.0, and remember, molarity times volume equals moles, and so if I multiply 1 by 0.5, we're going to get 0.5. So here, I'm sorry, I said 0.5, I meant 0.05, just like this is 0.03. So I'm going to have well, let me back that up. This is 0.03. This is going to be 0.5 moles. So I have 0.5 moles of this, and I have 0.5 moles of this. So what does that mean? Well, the 0.03 moles are going to be gone, right? Then you're going to subtract the 0.03 from this, you end up with 0.4, oops. We're going to subtract 0.03 here, and we're going to add 0.03 here. And what's that going to end up with? We're going to end up with 0.47 here, 0, and 5.03. So this is what we really need to be able to determine what we actually have at equilibrium. Now, let's take a look. Do we have any HF? That's an acid? We sure do. So we're going to write over here that our acid that we have is HF. Now let's take a look at our bases. We have OH minus, not so much, it got all used up. Do we have the conjugate base of the HF, F minus? Well, we have 5.03, so we for sure have that. So we're going to write F minus in here. And then for the others, again, we are not going to include water in this, but if we were doing it on an exam, they asked for all the species that were on there, we would include water. But we have Na plus. Now the Na plus doesn't do anything from this side. It's an Na plus on this side, and it's an Na plus on this side. It's a spectator ion, but it is in the water, and they want to know what other things are in there. So we're going to write Na plus. So the reality is that anytime that we're dealing with ever a strong base being added to a weak acid, or a weak acid being or a strong acid being added to a weak base, the first step is always to do the stoichiometry. So hopefully you're getting used to converting things into moles or millimoles in the first step and seeing what's left over. And then once we see what's left over, we go on from there. Hopefully this has been helpful.